Recording. All right, sweet. Recording started. So let's see, today's Thursday. So we're going to have a review day today in preparation for the exam, which will be on Monday. So no class on Monday. The exam will be posted to Blackboard at like 8 or 8:30, so that if you want to, you can use our class time to work on the exam. Let's see, I've written the exam. Oh, I also posted, hang on. I should just write this down so all of it's on the screen too. So the exam's on Monday from 8:30 a.m. to 9 p.m. Okay, so please note that this due date, 9 p.m., is different than our usual 11:59 for homework. Okay, and I'd like everyone to submit their homework on Blackboard as a single PDF. Okay, so if you want to print out the exam, or if you want to just look at the exam on your computer screen and write down your answers on paper, whatever's fine. I just need it to be in a PDF form, and rather than having like 6 PDFs for each page, I need one PDF that's 6 pages long. And that will really greatly help me to be able to grade your exams in a timely fashion and give you guys all feedback, because I want to be able to, write on your exam so that you guys can see where you guys made mistakes, and you have some kind of feeling like the grade you get is justified. So that's about the PDF. There's a practice exam on Blackboard as well. And there's also a solution guide on the YouTube channel. Okay, so again, practice exam is not meant to be the way that you study for the exam. It's just meant to be something to help give you kind of an idea of where you stand. I really recommend that if you do the practice exam, try the practice exam in its entirety on your own first, then go to the solution guide and review your exam and grade yourself and see how you did, and use that as a way to sort of see which areas in which maybe you're a little bit deficient and target your studying in that direction. The practice exam doesn't have everything that we've learned since exam 1. It can't possibly have everything, just because of its length. So you should also check your homework assignments. Go back and maybe look at the homework assignments which gave you trouble. That's a good way to study as well. So that's practice exam. I don't think I have one more announcement. I guess there's still a homework due tomorrow, so please make sure that you do that homework assignment. I'll post a new homework today that'll be due again on the same usual schedule. It'll be due next Friday, but it'll cover material which we learned this week, which will be incorporated on the exam. So it might be good to take a look at that and check out some of those problems just to prep yourself for the exam. Okay, so that's all I have to say about announcements, I think. So the rest of today is just going to be a review day. And that means that the rest of the time is really your time to ask any questions that you guys have about the class. So for example, if you're confused about one particular topic, like you don't know how to do transformations of exponential functions, you could say that, and I can give you my spiel on the subject, Or if you have something more specific in mind, like a particular problem you found in the textbook, you can fire that off as well. So I guess without any further ado, does anybody want to start and get us kind of kicked off here? Can we do an example of graphing both an exponential function and a polynomial? Sure. Okay, let's start with, these are my notes. Oh, that's stuff too. Okay. Yeah, let's start with an exponential function. Let's try graphing f of x equals 3 to the x plus 2 minus 1. Is that complicated enough, or should it be more complicated than that, Sam? I think that's fine. Okay, cool. So let's see how we're going to graph this thing. We can kind of use the usual method, which would be to just, make a table of values and get some x values and get some f of x values and then just plot those points. Or we can kind of think about this through the lens of saying, well, I know this is an exponential function. I know that 3 to the x goes through 2 points. What are the 2 points that 3 to the x goes through? Anyone can answer, it doesn't have to be Sam. What are 2 points that 3 to the x goes through? Just any exponential function that's not transformed. We know there's 2 points that are definitely on the graph of that function. Yep, 0, 1 is definitely on the graph of this function, right? Because just consider plugging in 0 in for x here. We'd have 3 to the 0, obviously, is 1. Maybe not so obviously. Shouldn't use that word in math. But if we plug that in, we get 1. And there's one other kind of very clear point that's going to be on the graph of 3 to the x. Can anyone give it to me? Yeah, 1, 3 is the other one that's kind of sort of obviously on the graph of 3 to the x. And so what we can do now is one of two things. We could just take this thing and get some x values, plug them in, and then plot them on the coordinate plane, and then kind of have an idea of what this thing looks like. Or we can consider this function 3 to the x plus 2 as a transformation of 3 to the x. And how is it transformed? It's transformed down 1 because of this minus out back. And what does this plus 2 inside the parentheses give me? How is that going to transform the graph? Yeah, to the left 2, right? If we have a plus, this is kind of like the inside. Remember when we learned these transformations, when we have a plus 2 sort of with our independent variable, okay, you can think of there being parentheses here in this exponent. Okay, when we have that plus 2 inside our parentheses there with our x component, that's going to shift us horizontally. And the one thing we have to remember is that the plus is always kind of like not what we think it's going to be. We think, plus out back does move us up, but plus on the inside actually moves us left, which is a little bit unintuitive. So this is going to move us left too. And now I can take the following information. I know that 3 to the x goes through 0, 1 and 1, 3. So I know that 3 to the x plus 2 minus 1 goes through these 2 points, except I'm going to move them down 1 and left 2. Well, if I move 0, 1 left 2, then the x-coordinate becomes -2. And then if I move the y-coordinate 1 to be down 1, well, that would be 0. And then I do the same thing with the other one. I know it goes through 1, 3, so the transformed graph, left 2 from x equals 1 would be -1, and then down 1 from y equals 3 would be +2. And then I can just go ahead and graph those here. So here's -2, 0. I'll use a different color, and then -1, 2. So I know it goes through these 2 points. And then there's only one thing that I should really consider beyond this in the service of making a pretty accurate graph, which is I should also consider where is the horizontal asymptote? Well, I know that 3 to the x has a horizontal asymptote at y equals 0, right? So 3 to the x plus 2 minus 1 has a horizontal asymptote at, and now I started with a y value, okay? So I should really be considering how 3 to the x plus 2 minus 1 has been changed from my original function in terms of the y values. So someone help me fill in this blank here. Where should the horizontal asymptote be for 3 to the x plus 2 minus 1? Should have another y value. Y equals what? Yeah, y equals -1. That's right, Sam. Okay, good. I like that we're getting some more participation in the chat. I like that. For the review day, it's kind of important for you guys to be involved in what we're talking about. So, as they say, math is not a spectator sport. So I hope that you guys are following along on your own paper at home or trying to solve these problems kind of as I'm doing them, or thinking about how you want to solve them at least. Okay, so we just know that there's going to be a horizontal asymptote at y equals -1. So I'm just going to draw something which looks like an exponential function. And it should have a horizontal asymptote here at y equals -1. And by horizontal asymptote, I mean we're getting very, very close, but never touching this horizontal line y equals -1. Okay, so that's how I can view the graph of an exponential function. Even though it's transformed, I can view it through the lens of these function transformations. Okay, so as long as I know how to graph, as long as I know how to graph y equals a to the power x, I can graph y equals C1, so that's a constant, C1, some number, C1 times a to the C2 x plus C3 plus C4. Okay, so I can just do these, put any number here, C1, C2, C3, C4 that are not 0. I can graph that just by considering them as the whole function as a transformation of my original y equals a to the x. Okay, and if you want to go the other route and do this x and f of x thing, that's fine too. We could plug in, like, I don't know, let's try -2, -1, 0, 1, 2. If we do -2, we'd get 3 to the 0 minus 1 would be 1 minus 1 would be 0. If we do -1, we'd get 3 to the -1 plus 2 would be 1. So 3 minus 1 would be 2. And then if we plugged in 0, we'd get 3 squared is 9 minus 1 would be 8. If we plug in 1, we'd get 3 cubed is 27 minus 1 is 26, and so on and so forth. You can go ahead and do that if you want. But you would probably want to do a couple more negative values in here, like -3 and -4, just to help you see where the horizontal asymptote is going to be, if you're not going to kind of view this as a transformation. Okay, so that's how we graph exponential functions. So I think Sam was the one who asked that. Are you satisfied with this explanation, or is there anything further that I could explain for this one? Okay, any other questions about this example for any other students in the class? Okay, if not, then we'll talk about how to graph a polynomial function. So let's pick a hard one. Let's graph, hang on. Let me use my Wolfram skills to give myself a good problem very quickly. It's supposed to be x. Okay, let's do this one. It's we'll try to graph x cubed minus 7x squared plus 15x minus 9. And why don't we call that f of x just for good measure? Okay, so here's what I want to do with a polynomial. Okay, first of all, there's two important aspects of the graph. First of all, end behavior, i.e., f of x goes to blank as x goes to infinity, and f of x goes to blank as x goes to negative infinity. Okay, so in the long run, if we have a coordinate axis, is our graph looking like up here and down over here, or are we having like maybe a graph which has behavior where really far to the left we're actually going up as well and up on both sides, or are we down on both sides, or what? Okay, so that's end behavior. And the other kind of important components of the graph of a polynomial are going to be the zeros. And depending on whether the zeros have multiplicity, even multiplicity, or odd multiplicity, we will either bounce off the x-axis or pass through it. Okay, so these are the major components of the graph of a polynomial function. Okay, and I think that you'll find that the trickiest part of this is going to be figuring out what the zeros are, because here we have a cubic polynomial. Okay, so the only way we know how to find all the zeros of a polynomial is to basically guess one of the zeros and then use long division. Okay, so that's what we're going to do. But first, let's determine what is going to be the end behavior of this guy. Okay, so let's figure out first, let's decide as a class what should go in this blank right here with my pink circle. I want to know what happens to f of x when x goes to infinity. And somebody maybe can tell me, what is the most important component of the polynomial for figuring out what the end behavior is? Yeah, you're right, Morgan, but can you expand a little bit on how you know? The minus. Not sure what you mean, Heidi. That's right. The a value is positive. Okay, so I can work with that. So I think what Morgan's getting at here is that we should be looking at this leading term here, and we should be looking specifically at what is the coefficient on that leading term. So we need to care about the coefficient on the leading term and the degree being even or odd. That was how we determined end behavior. Yeah, that's right, Abdul Rahman. Okay, so here's why. When x is getting very, very large, okay, the number that we get when we take x and we cube it, okay, when we take x and we cube it, this term is going to dominate all of the other terms by a lot, okay? Because if you consider what does the graph of x cubed look like, versus x squared, here's x squared, and here's x cubed. It just grows faster and faster and faster and faster, and this distance between the two gets larger and larger and larger the further we go out to the right. So as x goes really, really big, then x cubed is so unbelievably large that it's like, we're subtracting like a thimble full of water. This is our thimble full of water. I don't know if you don't even know what a thimble is. It's for sewing. You put it on your finger. It's very small. So this is like a thimble full of water, and here is our ocean. Okay, and if you pull out a thimble full of water from the ocean, then you haven't really affected it. Okay, so the point is when x is incredibly large, x cubed is way, way bigger than all of the rest of this stuff. Okay, so that's really the only thing that's going to determine whether we are soaring to the moon or going way down to the depths of, I don't know, somewhere very deep. Okay, so that's why we care about the leading term. And then when x is very, very positive, it doesn't really matter whether this power here is even or odd, right? We're just going to be going to infinity by virtue of the fact that the coefficient is positive, okay? So you just need to worry about what is limit as x goes to infinity of x cubed, basically. And that's equal to infinity. And for this second one, what we're going to consider instead is we're still going to just worry about the leading term, but we're going to consider what is the limit as x goes to negative infinity of x cubed. Well, if we take a negative number and we cube it, we still have a negative number. So this number is going to be getting very, very large and negative. So we call that negative infinity. Okay, so we have a cubic polynomial, and we determined that our end behavior on the left is we're going to be going down, and our end behavior on the right is we're going to be going up. Okay? So we just need to consider what's happening with basically the leading term for the end behavior. Okay, then we've got the zeros. Okay, so for the zeros, what I'm going to do, I already kind of mentioned. Why don't I use that other blue? This blue is better. For the zeros, what I'm going to try to do is I'm going to try to guess a zero for x cubed minus 7x squared plus 15x minus 9 is equal to 0. And then I'll try to guess a factor. Well, I'll guess a 0, get the factor, then use long division. So can anybody see kind of off the cuff one of the zeros of this polynomial already? Something that we could plug in for x that would make this equation 0? Yeah, that's right. So the factor is going to be x minus 1. We can plug in 1. Let's try 1 cubed. So the first step here, okay, for guessing a 0, you should just immediately try 1, -1, 2, and -2, and I will never give you something where these are not a factor. Okay, I'm just not going to do that. So we get 1 cubed minus 7 times 1 squared plus 15 times 1 minus 9. Well, that's equal to, well, 1 minus 7 is -6, plus 15 minus 9 is 6, so this is -6 plus 6 is equal to 0. So x equals 1 is a 0, and we know that's true if and only if x minus 1 is a factor. Okay, so we're going to set up our long division with x cubed minus 7x squared plus 15x minus 9, and we're going to long divide out x minus 1. Okay, and I'm going to go through this long division a little bit quickly, but just stop me if it's too fast or if you get confused on one step. Okay, so the first step is I want to figure out what do I get if I divide my leading term of my of what I'm dividing, which I can't remember the term right now for dividend. I think it's the dividend divided by the leading term of my divisor, and that's how I get the first term of my quotient. Okay, and then I subtract, and I always subtract with these parentheses because I need to remember to distribute that minus sign. And what I'm going to put in here is going to be what I get if I multiply x squared times my divisor. So I get x cubed minus x squared. What does this become? Well, the x cubed cancel by design. We chose x squared so that they would cancel. And then what are we left with? We do negative 7x squared minus negative x squared gives us 6x, negative 6x squared, plus 15x minus 9, and then we just keep going with this process. The next thing I need is negative 6x, and then I subtract negative 6x plus 6x squared plus 6x. Okay, by design, negative 6x was chosen so that these would cancel. And then we're left with 15x minus 6x is 9x minus 9. And you can see already this is going to work out flawlessly. We just have to multiply now by 9. And we subtract 9x minus 9 from 9x minus 9, and we get 0. So our long division worked out. But we knew that it would work out because we chose something which we already knew to be a factor of our polynomial. So at the end, what do we get? We get that x cubed, what was it, minus 7x squared plus 15x minus 9 is equal to 0. And we can restate this problem as x minus 1 times x squared minus 6x plus 9 is equal to 0. And then we can factor this using regular factoring. So let's do it. We just get x minus 1. And what should my factors be for this x squared minus 6x plus 9? How does that one factor? Yeah, negative 3 and negative 3. We get x minus 3 and x minus 3. Okay, or I could write that as x minus 1 times x minus 3 squared equal to 0. And this is going to give us two zeros. It gives us x equals 1 as a 0, or x equals 3. And there was one other thing which I needed to consider with my zeros for the graph, and that was whether the multiplicity was even or odd. Okay, so here the multiplicity of x equals 1 is just 1, okay? It's the power of the factor, which is odd. And then the multiplicity of this 0 is 2, which is even. And now we have everything we need to know to graph this thing. So let's give ourselves a coordinate plane. Okay, and here's 1, 2, 3. And what do we know? Okay, the first thing that we found out was that very far to the left, we're going down. Okay, we're going down very far to the left. And we also know that we're going up very far to the right. And we know that we have a 0 at x equals 1 and a 0 at x equals 3. And we know that at this 0, we're going to pass through because the multiplicity is odd. And we know at this 0, we're going to bounce off. So all I have to do now is connect the dots, okay? So here's how I'm going to connect them. I'll move that a little bit more like that. So first off, I'm going to come up here to my initial 0, okay? I can't possibly go up like this because otherwise this point here would be a 0, and I solved for all of the zeros, and I know that negative whatever is not a 0, so I'm not going to draw it like that. I'm going to draw it coming up through my first 0, and then I should be above the x-axis for a while, and then eventually I need to come back down and hit that 0. And rather than going through, I know that since the multiplicity of that 0 is even, I should bounce off. Okay, so I just come down like this, and then I know that eventually I need to wind up connecting up towards this top right region, so I'm just going to connect those like this. Okay, and here's a very rough graph of what this thing looks like. If you want to see what it actually looks like, we can put it in Desmos. So let's see what we get. What is it? X cubed minus 7x squared plus 15x minus 9. So x squared minus 9. Okay, great. And so here's what we see. This thing is definitely going way down to the left, way up to the right. And in the middle, what do? We pass right through this 0 here at x equals 1. We go through, and then we come back to 3, and we bounce off. And then we go off to positive infinity. Okay, so you're going to notice my graph looks different than this one. But what's important for the graphs to share is the zeros, the behavior at the zeros, and the end behavior. That's what we need to make sure we get right. Okay, so that's how we graph a polynomial. So how are we feeling about that example? Is that pretty clear? You feel like you could do this on your own? Okay, good. All right. Well, I think that was all that Sam had asked about graphing. So we can move on and talk about some other topic now. So does anybody else have something that they kind of came prepared to ask about? I know some students put on their exit slips every now and again. Oh yeah, sure, we can do one with hold. Yeah, no problem. Okay, so first of all, the context of when we have a hole in the graph of a function is always when we have a rational function. And why don't I say holes in graphs of rational function? Graphs of rational functions. So I have f of x, my rational function, is equal to n of x divided by d of x, where n of x and d of x are polynomials. Okay, so I have integer powers of x in the numerator and the denominator. Okay. We have a hole in the graph of x, in the graph of f of x, whenever, and I'm going to write this in a slightly different way. I'm going to write n of x we have a hole in the graph of f of x at x equals a. Whenever n of x divided by d of x is equal to x minus a to the power m divided by x minus a to the power m times q1 of x and q2 of x. And q1 of a is not equal to 0. q2 of a is not equal to 0. So what am I really saying here? I'm just saying that we have a hole whenever x minus a is a factor in the denominator and a factor in the numerator, and they have the same multiplicity. Okay, they have the same multiplicity in the numerator and the denominator. So for example, f of x equals x minus 1 times x minus 3 divided by x minus 3 has a hole at x equals 3. Okay, so it's when basically we can cancel a factor from the numerator and the denominator. Okay, that's when we're going to have a hole. And so here's how we kind of think about this. We know as long as x is not equal to 3, then we know that f of x is just going to be given by the numbers which we get when we do x minus 1, and then we multiply that times the number x minus 3, and we divide that by the number x minus 3, and we can just go ahead and cancel these guys straight away, since we know we don't have to deal with dividing by 0, and we just get x minus 1. So as long as x is not equal to 3, the graph of f of x is going to look just like f of x equals x minus 1. But, when x equals 3, f of x is going to be equal to, strictly speaking, x minus 1 times 0 divided by 0, which is 0 divided by 0, is not defined. Okay, so if we were to graph this thing, what would it look like? Well, it would just look everywhere like x minus 1. Okay, so I'm just going to put my y-intercept here. And why don't I put some 1, 2, and 3. And I know that the function should pass through those 2 points here. So this x minus 1. And if we just connect the dots, except there's one caveat, which is that we should have a hole here at x equals 3. Okay, so that's an example of how this whole business works. Okay, which is to say basically that if we consider actually putting in an input into this function, and we just consider that this input is not equal to 3, then we can just go ahead and cancel those terms and move on with our lives. The only time that we can't really cancel those terms is when we have 0 divided by 0. For example, it would be kind of bad bad mathematics for us to try to cancel these two zeros and say this is equal to x minus 1. Okay, we can't cancel zeros like that in the same way that we can cancel other numbers. Okay, we have to treat 0 with a sort of a special treatment. Okay, so I think we've learned extensively at this point in our mathematical careers that we can't divide anything by 0, and 0 divided by 0 is even more bad than dividing some other number by 0. So let's see here. So the whole is at the value that makes both n of x and d of x equal to 0. Yes, you're exactly right. Except in the case when you have something like okay. So this is not really so important, and I'm definitely not going to focus on this on the exam, but I'll quickly say if the multiplicities don't match, we might have an asymptote. For example, if we had f of x equals x minus 1 times x minus 3 divided by x minus 3 squared, this function has an asymptote at x equals 3. But the most important thing to know is that, well, the function's just not defined at x equals to positive 3. Okay, so we want to see these multiplicities here match if we're going to have a whole, because when they match, then we can just go ahead and cancel them completely, and then we would just be left with x minus 1. However, if we had this 2 here, when we cancel this, we would actually wind up with x minus 1 over x minus 3 whenever x is not equal to 3. And this function has an asymptote at x equals positive 3. So if the multiplicities don't match, we're in a bit more of a complicated scenario. Okay, but I'll give you the information now that if I give you a whole problem on the exam, the multiplicities will match, and it will be something more simple like this. So this is just to satisfy your mathematical curiosity, Sam, and to answer your question in a complete way. Okay, so have I explained the wholes to everyone's satisfaction, or is this still sort of confusing for people? Totally okay if it's more confusing. Oof, can we do an example of graphing a rational function? Yeah, we can. Let me come up with one that doesn't look horrible. Okay, yeah. Why don't we do this one? No, that's okay. It's just sort of, it's tricky to do this on the iPad. And it's a little bit hard to come up with examples sometimes, but we'll make it through. Let's try graphing this one. Okay, x minus 3 squared divided by x minus 1. Okay, and I'm just going to go through each thing here. Okay, first of all, let's check. Do we have any zeros? Yes, we have zeros. Where are they? Where is this function equal to 0? We have a rational function. We have some number divided by some other number. If this is equal to 0, then the top number has to be equal to 0. So when is my numerator equal to 0? Yeah, x equals 3. Okay, so we've got a 0 at x equals 3. In fact, we even know it's multiplicity 2. All right, how about a horizontal asymptote? Am I going to have a horizontal asymptote? Does anybody remember what determined whether we had a horizontal asymptote or not? Undefined is kind of on the right track. Yeah, N and M. And yeah, Heidi, you've got it. No, we're not going to have a horizontal asymptote. And the reason is what we care about for whether or not we have a horizontal asymptote is what is the degree of the numerator and the degree of the denominator. Well, the degree of the numerator here, if we were to FOIL out x minus 3 squared, we get a quadratic. It's 2. And the degree of the denominator is 1, which means as x gets really large or really negative, this top term is going to sort of dominate the bottom term. Okay? So, no horizontal asymptote. In fact, we could even say a little bit more. We can say that the limit as x goes to infinity of x minus 3 squared over x minus 1 is equal to infinity. And we can say that the limit as x goes to negative infinity of x minus 3 squared, well, x minus 3 will be some really large negative number, but we're squaring it, so it'll be positive. And the denominator will just be another large negative number, but peanuts compared to x minus 3 squared in terms of absolute value. So this is going to negative infinity. Okay, so we even know the end behavior. And how about vertical asymptotes? Any of those? For x minus 3 squared over x minus 1? Yeah, vertical asymptote at x equals 1, yes. Okay, now let's analyze what is the behavior. What's the behavior near x equals 1? Well, to analyze the behavior near x equals 1, what we want to check is what is the limit as x approaches 1 from the left of x minus 3 squared divided by x minus 1. And if you want, at this point, you could go back to my lecture, and check that, or check the notes and find our table, and you'd be able to use the, find the a value or whatever, and check whether it's positive and whether the multiplicity of the 0 in the denominator is even or odd, and you could check and see what that behavior is. But if you're working on the fly, you can just use this method and check what is the limit. So we want to consider what's happening to this number when x is very, very close to 1, but less than 1. Well, if it's very, very close to 1 and less than 1, the top is going to be something like it's going to look like negative 2 squared divided by some very small and negative number. Okay, and why is it negative? Well, if x is less than 1, then x minus 1 is less than 0. So that's why this denominator will be a really small number. And if we take negative 2 and square it, we get, this is going to look like 4 divided by a small negative number. So we'll write that as negative small. How about that? We take a positive number and divide it by a negative number, which is extremely small. We're going to get something which looks like negative infinity. Okay? That's what's happening. So we know that this limit is actually equal to negative infinity. Likewise, we can check what's happening when x approaches 1 from the right. X minus 3 squared over x minus 1. Well, the top is again going to look something like 4. It'll be a little bit bigger than 4. And the bottom, what's happening to the bottom? X is slightly larger than 1. So x minus 1 will be slightly larger than 0. So this bottom number will be some small number, but positive. And this is going to, if we take 4 and we divide it by successively smaller and smaller and smaller positive numbers, you can try it. Try doing like 4 divided by 0.000001. You'll get a really big number and positive. So this whole thing is going to infinity, positive infinity. So what's the behavior look like near x equals 1? It should be going down to the left and up to the right. Okay, and now I think we have all the tools that we need to actually graph this SOB. So let's put on a couple of points. How about here's 1. I guess we just need that 1 point, really. So we know we're going to have a horizontal asymptote. Not a horizontal asymptote, a vertical asymptote at this line, x equals 1. And what else do we know? We know also that x equals positive 3 is a 0. So we know our graph is going to pass through this point right here. And we even know that it should bounce, since our multiplicity of that 0 is actually our multiplicity of that 0 is even, right? X minus 3 squared. It's an even multiplicity 0, so it should have bouncing behavior. There's no horizontal asymptote, but we do know the end behavior. We know that the limit as we go to positive infinity will be positive infinity, and the limit as we go to negative infinity will be negative infinity. So we can also fill in, we know that the end behavior should look something like this. And on the left, it should look something like this. And now we can just fill in the behavior of what's going to happen to the left and to the right of our horizontal or our vertical asymptote. Okay, we know we should be going up on the left hand or on the right hand side of this, and we know we should be going way, way down on the left hand side of this. And now what I'm going to do is just connect the dots, basically. I'm gonna do my best to connect the dots. So this one's going to come down like this, and it's going to touch this 0 and then bounce off, and then it's going to go way off to wherever. It's going to positive infinity as we go very far to the right. And on the other side, well, I've got these two pieces. I just kind of want to connect them nicely. I know my graph shouldn't pass, say, above the x-axis like this, because I know that there's no zeros on this side of the x-axis. I know there's only one place where the graph crosses or touches the x-axis, and that's when x is equal to 3. So I know we should stay completely beneath the x-axis because of that. So I'm going to draw something which looks something like this. I don't know. This may not be that accurate. It doesn't matter. What matters is we've identified the asymptote correctly. We have the right kind of behavior near the asymptote. We pass through or bounce off of all of our zeros, and we have the end behavior right. Okay, so this graph is not going to be perfect, but it's going to have the right kind of features that we care about. Am I picking test points? You mean for these limits here? Is that what you're talking about, Sam? Yeah, you can think about it that way. But what a limit really is, when I write limit as x goes to 1 from the left of x minus 3 over x minus 1, x minus 3 squared over x minus 1, means what I'm talking about is if I plug in x equals 0.9 and then x equals 0.99 and then x equals 0.999 and then x equals 0.99999, right? Like going on and on and on and getting very, very close. X is getting close to 1, but still less than 1. What I'm talking about here is if I then plug this into f of x, and I get f of 0.9, and then I get, f of 0.99, and then dot, 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 f of 0.999. What I'm saying when I mean this limit, what I'm talking about is that here the process is that x is getting very, very close to 1, and I can keep plugging in these values into f of x, and I can say f of x is getting close to some number L, where L might be infinity. And this number L is what I mean when I write limit as x goes to 1 from the left of x minus 3 squared over x minus 1. Okay, this is what it means to take a limit. So you can consider, if you plug in something like x equals 0.999, it's probably going to give you a pretty good idea of the behavior if you know that it's going to either positive or negative infinity. Well, that's the thing, is I didn't really... Yeah, this is kind of hard to explain. Maybe I can explain this with the following example. Let's try doing this. Let's try doing limit as x goes to infinity of 2x divided by x. Okay? And what I'm going to do here is I'm just going to plug in successively larger values of x, like x equals 1, x equals 10, x equals 1,000, dot, dot, dot. And what I want to look at is what's happening to 2x over x. So this is x. And then we'll look at 2x over x. Well, if I plug in 1, I would get 2 over 1 is equal to 2. And then the next number would be 10, so I would do 20. Oh, what am I doing? 2x over x. Maybe I should do like 2x over x squared. 20 over 100 would be equal to 0.2. Then x equals 1,000, what would we get? We get like 2,000 over 1,000 squared. would be something like 0.0002. And my point is the following. When I write down the limit of this thing, okay, I'm not actually really thinking about taking one of these numbers and plugging it in and seeing what I get. What I'm considering is that this number on the left is getting very, very close to infinity, and this number on the right may or may not be getting closer and closer to some number L. Okay, and when I write this limit here, I'm talking about the number L, which these are getting very, very close to. Okay, but if I pick any individual value for x and plug it in, I'm never actually going to get L, because L is not something that's actually going to be achieved by the sequence. I'm just saying that the sequence of numbers here is getting very, very close to the number L, which in our case is 0, right? So when I talk about the limit, I'm kind of asking not a question about where have we been and where have we gotten, but where are we going? Does that make sense? Or is this totally abstract? Okay, so when I write this stuff up here about these limits, I just want to consider what's happening to the number in the numerator and the number in the denominator. So let's focus on this case here where we went to 1 from the left. Well, what's happening is that the top, as x approaches 1 from the left, the top is getting very, very close to the number -2, okay? Because the x is getting very close to 1, so 1 minus 3 would be getting very close to -2. And then the denominator is what we kind of care about. When x is getting really, really close to 1, but less than 1, this thing, x minus 1, is going to 0. But very importantly, it's going to be a very, very small number, but it'll be a negative number. And the whether or not it's negative is really what we care about the most. Okay? So if we consider a sequence of numbers which are negative and going to 0, okay, something like negative -0.1, -0.01, -0.001, okay, and we consider the sequence 4 divided by -0.1, and then 4 divided by -0.01, and then 4 divided by -0.001, and so on and so forth. We know that this left-hand side is approaching 0, and I can see by looking at the right-hand side, if I take this number 4 and divide it by successively smaller negative numbers, these numbers are going to be like, this one will be like -40, this one will be like -400, this one will be like -4,000, and so on and so forth. And I can see that what's happening is that this number on the right side is getting very, very close to, well, it's just going to -infinity, right? The smaller x values that I choose that are still negative, as x approaches 0, then f of x will be getting unbelievably large and negative. So that's how this limit business works. Okay, I think that's about as well as I can describe that. But if you don't want to use the limits whatsoever, okay, and this is kind of an intuitive way of thinking about things, if you don't want to use this, then I'd recommend referencing the notes, okay, because we made a big table of how you can determine the behavior near an asymptote without really having to think about what the limits are. I showed you how we use the limits to figure out what the chart should have in it, but ultimately we had 4 different types of behavior depending on the value of like some constant a, which we defined to be like the rest of our rational expression and the multiplicity of the 0 in the denominator. And we have 4 different cases and 4 different colors and behaviors near the asymptote. So if you're not so comfortable with working with those limits, that's fine. You can just go back and reference that chart. Okay, so we got 5 minutes left. I probably have time to do one more example for us. So does anybody have anything else that they'd kind of like to check out? All right, if not, then I'm going to finish up with a couple of random examples, which I pulled from various other exams that I found. Aha, like this one. So forget about sketching. Let's try to answer the following question. We have a function which is a quadratic function, and we want to know where is the vertex of f of x. Okay, so we have f of x equals x squared plus 6x plus 9. And what I'd really like to do in order to find the vertex of f of x is to write this, is to do some funny business, and then ultimately write this as something like f of x equals x minus h squared plus k. And then I will know that the vertex is at the point h comma k. Okay, if I can put this into vertex form, then I would know I would know where the vertex is just by virtue of looking at this number h and this number k. Okay, and the way we do that is by completing the square. Okay, so here's what I want to do. I want to kind of set this 9 aside. And I want to focus on these first 2 terms. Okay, the quadratic term and the linear term. And what I'd like to do then, oh, actually, this is already a perfect square, isn't it? Oh yeah, this is already a perfect square. So I don't even need to complete the square. This is just x plus 3 squared, isn't it? So we get f of x equals x plus 3 squared, which means that my h value here is negative 3. And my k value is 0. So that tells me that the vertex is at negative 3 comma 0. So that was even easier. I didn't even have to complete the square. But let's see how we would do it if we really wanted to. We could try x squared minus, I don't know, minus 7x plus 12. Let's try this other one so that we can see how we complete the square. I'm going to take this 12 and set it aside. Oh man, I shouldn't have picked this one either. I'm in trouble now. Here we go. That'll work. I'm going to take this 8 here and set it aside, and I'm going to focus in on these guys. So to complete the square, I should take the coefficient on the linear term in our case, -6, divide by 2 and square it. So if I take -6 divided by 2 and I square it, I get 3 squared, -3 squared, which is going to be equal to 9. And what I'm going to do now is a clever trick. I'm going to not change f of x, but I'm going to rewrite it in this clever way, where I write x squared minus 6x, and now I'm going to add 9. I'm going to put all that in parentheses, and since I added 9, I'm also going to subtract it. And I've still got my 8, which I left set aside. And now what I can do is recognize that this side in here is going to be a perfect square. I can rewrite that part as x minus 3 squared. And then I just combine the -9 and the 8. That'll be -1. And this is how I've gotten it into vertex form. This means h is equal to 3. K is equal to -1.
Last training.
Therefore, the vertex is at 3, -1. Okay, sorry, I went over by 1 minute, but I just wanted to give you guys that last example. So we'll close here for today. But if you have any further questions, I'd encourage you to either stick around and ask after class. I can stay here for probably another 10 minutes. Otherwise, please email me and we can meet together sometime for some extra office hours. If students are strongly in favor of an extra office hour tomorrow sometime, I can make that work. Just email me, okay? All right, so that's it for today. Sorry for going over. Yep, have a good weekend.